Hi, everyone. My name is Susan Pakin, and I'm a senior research specialist with the Center for Spatial Data Science and the Healthy Regions and Policies Lab. And I'm going to be talking with you all today about how to calculate spatial access metrics in Python using this interactive tutorial in this Google Colab notebook. So before we get started with the notebook, I just wanted to contextualize the work that we're doing today and you're focusing on this week around access. Access is a really important measure and concept to incorporate in lots of different research and different real life applications. Here we're going to be talking about spatial access. So here we're going to be talking about how long does it take to get from point A to point B, and we'll delve a little bit more into the details of that momentarily. But also we can think of access in a lot of other dimensions, such as accessibility in terms of being available and usable by people with differing abilities, or accessibility in terms of affordability, and are people able to afford buying certain items at a certain store or in a certain area. So again, today we're going to be talking about measuring accessibility in terms of time and also in terms of the number of resources in a given area. But this concept can be applied in lots of different research areas or questions as well. So let's look at the tutorial. So I'll be going over the environment setup within your Google Drive, then going through cleaning and processing the data that we'll be using in the tutorial today. And finally, calculating the access metrics and then saving your final data set. The bulk of the tutorial will be cleaning and processing the data, but let's get started. So I'll just say this tutorial assumes some familiarity with Python and also the Colab setup, but we walk you through everything here. You don't need any prior Python coding skills. I understand most of you have a bit of background in R, and that'll really be a big help as you work through and understand the code here. So the environment setup is a really important part of this piece. To run this notebook, you need to copy all of the content from the Access Metrics tutorial folder, including this Colab notebook, onto your own drive. So to do this, follow these instructions, and I'm just going to walk through this with you. So first, go to this Access Metrics tutorial folder. Okay. So this is what you should see when you're looking at the Access Metrics tutorial. So I'm going to Control A. I'm going to go to make a copy. Copying 6 files. Copied 6 files into my drive. Great. Then I'm going to go to my drive. I'm going to take these 6 files that I'll say copy. And I'm just going to say move to, and this is really important. I'm going to create a new folder and call it Spatial Access, spelled exactly like that with the underscore. Press the checkbox, move here. And we've got a folder called Spatial Access with 6 files in it. Now, each of these files says copy of, and this is annoying, but this is how Google Drive works. We're just going to take out that copy of name. So we're just going to rename everything. Just removing copy of. And the last one. Okay, so it's really important. All of these are labeled exactly like you see here. You've just deleted the copy of. So then now you have this script saved on your drive. So this is what I recommend working with because you'll be able to add any comments or edits within your own copy of this that won't affect anyone else. So now you've reopened the script. We've done the environment setup, and now we can move into packages. So we're going to be using 5 main packages in Python for this analysis. We're first going to start with the spatial index package because it's a dependency for the spatial access package. This spatial access package is what allows us to calculate the driving time and the count or number of resources within a threshold variable that we'll be building up towards calculating. So we're going to run. Colab makes this super easy to run. If you've never used Colab before, you see each of these little code chunks, and you can just press the play on here. It should say, if you hover over, it should say that the play means run cell, and it says cell has not been executed in this session. And it tells you the last person that executed it. So let's press play. Some of this already has a preview coming up for me because I've recently run through this. So you get a little preview, you'll see here. Okay, so that's run. Next, we're going to install the spatial access package. This sometimes takes a minute. This says sometimes there are some issues with compiling this package due to older versions of the dependencies. We'll see an error that might come up. Might not come up here, but let's see while it's installing. And if there is an error come up, these are instructions for how to work through that. And it shouldn't be an issue once you run it again. All right, so we're getting that. This is the error to be expected. Just press restart runtime, click yes, and then press the play button once again. Great. And I'm just gonna press. Next, we're gonna just install GeoPandas Python package and import these Python libraries. And now we're gonna make sure we've got our working directory set up. Our working directory is that spatial access folder that we just set up in Google Drive. So this says, make sure you already have the copy of the spatial access folder on your drive. And then once the folder is created with all 6 files successfully copied in there, we're going to run this code. It's going to generate a link. We'll follow the prompts, copy and paste the authorization code, enter, and we should see a successful drive mount. So I'm going to run this. Go to your URL. I'm using this other Gmail account. So then we're going to copy this code. This is our authorization code. Hit enter. And we are mounted. So basically this means that we're going to be working in this folder that we just created. It should be in your drive. All right, now we can get into the data now that the environment has been successfully set up. So all of the data that we copied in here is what we're going to be using as input into running this analysis. So we're going to be calculating access metrics to the nearest medication for opioid use disorder, or MOUD, for every zip code in the United States. I should actually clarify, it's every zip code in the 48 continental states in the US. So we're not including Hawaii and Alaska. We've already pre-calculated centroids for all of the zip code tracked areas. And these will be the origins in our origin destination calculations. Note that these centroids are population weighted and are restricted to the 48 contiguous states. So we're going to run this code here. And we've just read in this geopackage file, contiguous US zip codes. That's in right here. So we've read in this file, and here we can see, looking at the head of the data frame, geodata frame, we've got GeoID, which is the zip code or zip code tract area. We have longitude, latitude, Y and X points. Population is, I believe, population. We're not going to be using that. State FIPS code. We're not going to be using this. And then the geometry. So this is the point of the centroid, the population weighted centroid of each zip code. So next, we're going to read in our destination locations. So the destinations are going to be a data set that includes all of the location of providers of medications for opioid use disorder, or MOUDs. And here in this tutorial, we're going to be focusing on providers of one of the three main MUODs in the United States, and that medication is naltrexone. It's extended release naltrexone, sometimes you see it as. And in this tutorial and elsewhere, if you do research on naltrexone, you'll also see reference to Vivitrol, and Vivitrol is just the brand name of extended release naltrexone. So if you see that, just know it's the same medication. Vivitrol is just a brand name. So we're going to read in this data set, this geopackage of US-wide MOUDs. And we're specifically going to filter by the category of naltrexone Vivitrol. So you see here, we're looking at the head. You're just going to see the naltrexone data. What we've done, I'm not going to highlight the whole thing here, but what we've done is we've filtered out the methadone and the buprenorphine categories of this data. And these data are all sourced from SAMHSA, which is the Substance Abuse and Mental Health Services Agency of a federal agency, US government. So right now we just have naltrexone and Vivitrol. So ID in order to do our calculation. So in the next section, we're going to read in our geometry files of the ZCTAs and then overlay our naltrexone point location. So first, we're going to read in the ZCTA geometry file. This is going to take a minute to load. And while it's loading, I'll just note that we're looking at zip codes because this is a pretty granular level at which to examine community access to different measures for the entire country. Census tracts are smaller still, but we run into some issues with geocomputation and just the number of census tracts in the US, and it's totally possible to do, but for the purposes of this tutorial, we're just going to be focusing on zip codes. So now that we have our zip code geometry file loaded in, we'll now overlay the naltrexone locations over those ZCTAs and identify which naltrexone location belongs in which zip code, just to make sure they match. So first, we need to make sure that both of these spatial data frames are in the same projection. So we're going to transform both of them into the 4326 EPSG CRS. So this is going to take a minute also, just because, again, we're working with a national data set. So there are thousands of zip codes across the United States. All right, great. So now they're both in the same projection. We can perform a spatial join and identify the corresponding ZCTA for each location. So we're going to run this join here. And then we've got this new data set called deaths over. So here in this data set, we have the name of the provider of naltrexone. We have their address, their zip code, and then the matching zip code with the GeoID of the ZCTA. So I'll just note here, when you're working with ZCTAs, almost every single zip code aligns with a corresponding ZCTA. Like when we say zip code, we can use those terms pretty much interchangeably, except for a very small number of zip codes in which usually they're places that are very, very sparsely populated, or also some boundaries have changed for various to reflect different population changes or other like land use changes over the last 10 years. So we're trying to match, the zip codes provided in the addresses of the resource locations with the ZCTA geography here. And that's what we did here. So, this is sort of addressed in this comment here. You can see that some of the addresses overlap with different ZCTA boundaries compared to what's listed in the address zip code. You can actually check this by, if you comment out this line, this is kind of just like an extra bonus. It's interesting to see, but this is saying return which of the zip codes don't match the GeoIDs. And we see a few here. So we've got, in Missouri, this is slightly different than the GeoID. Same here. So we've got about 500 of these. You can see that some of the addresses overlap with different boundaries. We keep the data as is, like we don't want to take these out. It's still like overlapping and it looks about right. Like these are very similar digits and numbers. So it looks like they're in the right place. This isn't like a big data error, but this is something to consider if you're doing like a more precise or you need more precision, or if the accuracy like really matters for a particular place. So just something to note. We're not gonna take any of these out, but just to know for future analyses, it's always good to check when you're performing this type of merge or spatial join. So now let's do a little more cleaning and check. Let's do like a simple plot, a quick plot to check to make sure all of these locations are aligning with the ZCTA geometries. So these first two lines of codes are adding a latitude and longitude column from the geometry file. So I'm just going to run this. And then basically here, we're preparing the data to just do a simple quick plot again to check at what it looks like and make sure we're not seeing any resource locations out in the middle of the ocean or in Europe or something like that, because we should just be looking at the continental United States. So this sometimes takes a second. So we've got our data here. And scroll down, we're looking at this plot and it looks pretty good. That looks, about typical. You see a lot of clustering around major cities. You see, in the rural areas, there's fewer resources. This kind of intuitively makes sense. So we can go back and sort of like do more accuracy and precision checks. But for the purposes of this tutorial, we're gonna go with this data. It looks good. So we've done our sort of origin destination OD pairs preparation. And now we're going to start looking at the travel cost matrix. So in this section, we're going to load our pre-computed travel cost matrix. This is for all zip code tracked areas in the United States. This is something that our team at CSDS has been compiling and working on generating. And here we're going to be working with the zip codes, but we're also working on generating this massive data set for census tracts as well as counties. So we're going to load this file from our Google Drive. This is US ZCTA travel timetable. And we can just do a check here. Yep, we see it right there. So we're going to load this and then we're going to be filtering it for the relevant ZCTAs. So let's load this. great. And then we're going to filter it for the ZCTAs that are within the origin, that are our origins. So, excuse me, that are the destinations of the naltrexone resources. So that's what this chunk of code does here. So now that we have our filtered cost matrix, we are going to merge the travel cost matrix with the naltrexone destination and create the input matrix for access metric calculations. So that's what we're doing. We're reshaping that here. So we're going to run this. And then now that we've merged the destination GeoIDs with the travel cost matrix, we can drop that column and then use the ID variable that we had created before to identify each location instead of the name. So this is what we have here. So now we're going to do that reshaping that I just mentioned. So from long format to wide format, and we'll also be filling any of the missing values with NA. Or we're going to be filling in the missing values, and we're going to be using 999 to signify NA, which is a pretty common standard in data analysis and collection. So this usually takes a moment. So the reason why you see so much 999s is because these destinations are more than 100 kilometers away. And so they're essentially not accessible. So that's what that indicates here. You'll be able to understand that a little bit more at the end when we have our final data sets. So I'm gonna sort of just skip over reading this paragraph, but you can read this. It explains how we need to match the number of rows in the matrix to the number of columns in the matrix. And that's we need that for formatting purposes in order to use that as an input into our access model calculations. So we're going to pad the travel cost matrix with additional rows that's corresponding to the unmatched origin GeoIDs because some of them weren't matched. So you can use this here. And then we're reshaping this final cost matrix that we're going to be working with. So that's the travel cost matrix. So given that it takes quite a bit of effort to generate all of these matrices, we're going to save these as intermediate files for future use. We're going to use them momentarily as inputs into this next section. So run this code and it'll take a few minutes to compute, but we'll take a minute to run it and we'll be right back to calculate the access metrics. All right, so after we've saved our process data, it took me about 6 minutes to save that onto our Google Drive folder. We should see 3 additional files on your Google Drive folder. So intermediate destinations, intermediate origins, and transformed matrix. So these are all really important for the next step. So make sure that these are fully processed and saved on your spatial access folder in your Google Drive before moving on to calculating the access metrics. So we're going to use the process travel cost matrix to calculate, this says 3, but we're just going to do 2 today, 2 access-based metrics, driving time, and then count of resources within a particular driving time. So that's the number of naltrexone resources or provider locations within a set driving time. We're going to look at within half an hour driving time as like a reasonable measure of access. So the package that we're using called Spatial Access has 3 corresponding classes for these metrics. Access time, access count, those are the 2 we're looking at today. And you can just know that there's one more called access model, which is supposed to calculate like an overall comprehensive access score, incorporating the 2 other metrics and some other configurations as well into like an overall weighted access score. But we're just going to look at driving time and count today. So first, we're going to define the access metrics by providing the appropriate arguments, and then we'll calculate the metric, and then we'll save the final data set as a CSV file. So in initializing the access time and access count models in the spatial access package here, we need to ensure that the input data is formatted in a specific way that matches what the model can process. So this is information about, these are the details about sort of what is going into each of these models here. I'll let you read over that in your own time or come back to it. But this is how we're initializing these variables here. And then in the next section here, we're going to initialize the access time model. So we're going to call that access T. We're going to press play. We're getting this warning. It's still running, but you'll probably see this warning here that you should use TMX instead of CSV for significantly better performance. So it's still running here, but what this means is that sometimes the CSV is not the best suited format for this model and this type of calculation. So we're recommending initializing the model using our transform matrix CSV, but then resaving the transit matrix file as a TMX file. And we're going to do that. The code is right here to do that. And then reinitializing the model using the new TMX file. So that's just kind of a little bit of on the fly troubleshooting that we included here. So we're writing that as a TMX and then reinitializing this, and we are good to go. So now we have our access time. We should have our access time calculations. So now we're going to calculate our access count calculations. So we're going to run that. And again, that's basically taking the cost matrix, looking at the origins and our destinations. So now we're actually going to calculate the metrics now that we've initialized the models. Running this code block here, calculate. So for each of these, we're going to do access T calculate, access C calculate. And for access count, we're going to define the threshold, which is the driving time. So we're going to use the threshold of 30. It's set in minutes, so 30 minutes of driving time to indicate the half-hour limit that we want to set for this. So we could update that here with 60 minutes. We could say within 15 minutes driving time. That's where you would update that here at the very end. We're going to skip over the score, the access score metric. So now we're going to save, we've calculated those 2 metrics of driving time and count of resources. So now we're going to save that all into one beautiful CSV file, which then we can take and use as variables for mapping, for other analysis, for any type of geocomputation. So basically this is taking time to nearest, that's the driving time, and then count in range is our count metric. This categories is going to be, these are the variables. This is going to be replaced by the category that we selected, which is naltrexone. So we're going to generate this here. So we have time to nearest naltrexone, Vivitrol, count in range, and again, count in the 30-minute range. We know, and this looks, just looking at these numbers here, it looks about right. We've got time, like we've got, 90 minutes, 21 minutes. Anytime you see a 0 in time, that means that there is a provider within that zip code. So, in reality, it might reflect a very, it reflects an amount of time to get to the resource. But for the type of analysis we're doing here, just because we are doing centroid to centroid, know that when it says 0, that's not an error. That just means there's very good access, relatively speaking, to that resource in this zip code. So in the 99403 zip code, and that there's 0 travel time because the resource is in the zip code. So we can look at the CSV to double check, and we can sort of take this data and then read it into R or Python to actually explore all of the data. But we'll export this to CSV for now. So this ran, so we can check our spatial access folder now, and we should have, there we go. We should have our access to naltrexone. Sometimes it takes a minute to upload into the drive, but we have our access to naltrexone right here. I'm gonna just explore. This is gonna be a big data set, so it's gonna take sometimes a second. Again, it's nicer to be able to look at a big data set like this and read it into R, something like this. But basically what we have here are a really clean data set with 3 variables, right? So this is the ZCTA, the time to nearest, and the count in range. So in order to generate a map or a visualization with this data, all you would need to do is to merge this CSV with a ZCTA geometry file, and then create a chloropleth plot or run any other type of analysis on these variables. But it's really simple to just visualize this in like a simple chloropleth plot to look at some of the results here. And lastly, I actually did want to just show some of those maps because we are at the center, we're actually working on some research specifically looking at this topic but more broadly looking at access to all different MOUDs, all different, the 3 different categories and types of medications used broadly in the United States. So I just wanted to briefly preview some of our maps. So let me just pull these up here. So we can see here, this is over here, this is our driving time map. So you can see, this is big picture look at the United States. You see these bold borders here. These are dividing just the country into different census regions. So it's sort of easier to talk about what's happening in the South versus the Northeast, New England, the Northwest. This is for a forthcoming research paper. But you can see, blue is closer driving time, and red is over an hour and a half away. The dark blue is 0 to 14 minutes. And then it goes up to 90 or more minutes, which is very poor access. And sort of with the count, you see somewhat similar spatial distribution. You see a lot of clustering in the Northeast and in cities on the West Coast and scattered in the Midwest as well. But in terms of count, you're seeing, look at the way that this map is stratified. We're seeing much fewer resources in most of the country in terms of geography. So this is just sort of a check to evaluate if the data looks correct. And also, if it does look correct, then there's a lot of analysis that can come from this. So thank you so much for following along. If you have any questions, feel free to contact me. My email address is on the Colab notebook, and I hope this will be useful to you in the future. Good luck with the end of the quarter. Thanks.